this lab, we use paper chromatography on numbers of dyes and Kool-Aid. This lab helped us to identify the individual components of the dye or Kool-Aid of any mixture by using RF values.
The RF value of a mixture is its relative rate of migration. We calculated the RF value by running a mobile phase, water, through a stationary phase, chromatography paper. When the paper was placed in water, the water was drawn up through it by capillary action. The mixtures on the paper each had a different affinity for water and moved a different distance. The red dye had an RF value of 0.83. Both the green and blue dye had an RF value of 1. Kool-Aid 1 had an RF value of 0.53. Kool-Aid 2 had an RF value of 0.45. Finally, Kool-Aid 3 had an RF value of 0.35. We can also see that the chromatography separated two different components of Kool-Aid 3. Some components of the green dye may have also been separated, but it's hard to tell since it mixed with the red. This happened because the chromatography paper was bent when it was placed inside the beaker with the water.
Through the chromatography lab, we have made a conclusion through calculating the RF value that the green and the blue were the most polar and the Kool-Aid 3 were the most non-polar. And the reason why water molecules exhibit capillary action is because the adhesion to the wall is stronger than cohesive forces between the water molecules.
This happens because the space between cellulose molecules is small enough that surface tension and adhesion push the water up through the paper. As the water moves, it can carry mixtures with it. In this case, a nonpolar solvent is being used. Because of this, polar substances actually have a greater affinity for the stationary phase and not the mobile phase. Therefore, dye C would be the least polar. We can identify the unknown substance using its relative rate of migration. Dye A and the unknown substance both have an RF value of about 0.5, so they must be the same mixture.